The paradox of the Lorenz transformation, or what does the price of apples and bananas have to do with the space-time coordinates? On the surface, the question is pointless. But if we take a closer look at the derivation of the Lorenz transformation, we find that changing the price of apples and bananas can have a tremendous effect on the properties of space-time. Nonsense? No. The way of deriving the Lorenz transformation simply leaves much to be desired, and in fact, the Lorenz transformation in its present form does not have to be a correct coordinates transformation. Now we'll begin. According to the theory of relativity, the speed of light is constant regardless of the observer's motion. In order for the speed of light to be constant, the coordinates of moving bodies deform. The deformation ensuing observation of the constant speed of light is determined by the equation of conservation of the space-time interval. And for the case on the plane, it has the following form. This equation is practically the equation of a hyperbola, and the dimensional deformation relationship can be easily presented in a diagram. The Lorenz transformation formulas that determine how these coordinates are deformed are derived from the equation of conservation of the space-time interval. And all clear? Are there any questions? Well, let's try to look closely at the solution to the equation of conservation of the space-time interval. We will multiply and divide this part of equation by any two values, d square minus e square. The values of d and e are arbitrary and generally do not depend on the coordinates of time and space. They can stand for virtually any function and value. And we transform this equation and now we add and subtract 2ct x dE, and we obtain So finally we have transformed the space-time interval equation. And since the equation for the space-time intervals shows that ct square minus x square equals to ct prime square minus x prime square, so we are allowed to accept that the following relationship is satisfied. Or we can rewrite it in the following form. And this form reminds the already known transformation formulas. However, for e equals 0, there must be t prime equals t. And in the second equation, x prime equals x. So for the first equation, we choose the plus sign variant, and for the second equation, the minus sign. And finally, we get. And these are the equations that describe the coordinate transformations that satisfy the equation of conservation of the space-time interval. Since the values of d and e are arbitrary, we can assume, in line with the title of the presentation, that d equals the price of apples, e equals the price of bananas. In this case, our transformation, let me remind you, fulfilling the principle of the conservation of the space-time interval, has the form. Here, the coordinates t prime and x prime depend on the prices of apples and bananas. Note that when the price of apples is higher than the price of bananas, then the expression under the square root is greater than 0, and we have a transformation of coordinates that are real values. But if one day bananas become more expensive and their price exceeds the price of apples, the expression under the square root becomes smaller than 0, and then the solutions become imaginary. What does it mean? A change in the laws of physics that govern the world? End of the world? Certainly, as we know it. But the prices of apples and bananas have changed many times, and the world still remains as it was. Therefore, what about this principle of conserving the space-time interval? Let us consider another example. Now let d and e be any functions. They can be functions of any variables, but for the purpose of this example, we will assume that they are functions of time and space. This can be, for instance, functions f and g. In such case, transformations that satisfy the principle of conservation of the space-time interval take the form. If we want to have only real solutions, it is enough to add the following condition. Here the absolute value of function f is greater than the absolute value of function g. But still, with the freedom to choose the function, we have a practically infinite number of possible coordinate transformations that satisfy the principle of the conservation of the space-time interval. Okay, but what about the Lorentz transformation? If we compare the formulas for the Lorentz transformation with the general formula for all transformations satisfying the principle of the conservation of the space-time interval, it is easy to see that we will obtain the Lorentz transformation if we assume function f equal to 1 and function g equal to v by c. Thus, the Lorentz transformation is a special case of solving the space-time interval equation, and assuming that the Lorentz transformation is the solution to this equation is a great abuse here. So, what are our conclusions from our reasoning? First, the Lorentz transformation is not a solution to the space-time interval equation. It is only a special case of such a solution, while the number of solutions, i.e., the number of possible transformations, is practically infinite. Additionally, the relative velocity of bodies is in no way derived from the space-time interval equation. It is put into the transformation equation instead of the variable e, in exactly the same way as it was put in the same place the price of bananas. This velocity is a value that has nothing to do with space-time coordinates and is only inserted because its insertion yields the 19th century Lorentz transformation. Second, the example with apples and bananas, according to which a change in the prices of apples and bananas threatens to destroy the universe, shows that the application of the principle of the conservation of the space-time interval should be limited to a certain class of phenomena, probably wider than described by the Lorentz transformations, but not as wide as the space-time interval equation itself allows. For example, on the basis of my other works, I have come to the conclusion that the principle of the conservation of the space-time interval only makes sense for the problems of observing the same body by many observers, and it is only concerned with real solutions. It is described, for example, in the publication where I also show a coordinate transformation unambiguously resulting from the correctly applied principle of the conservation of the space-time interval. However, the interval equation cannot be used to describe the geometry of empty space, as it is in the case of the general relativity. According to this approach, such effects as tachyons, time travel and parallel worlds are exactly the result of applying the space-time interval equation beyond its scope of application in physics. So what? Can you now go to the professor who taught you how to derive the Lorenz transformation from the space-time interval equation and try to corner him? Nothing of that. After a short discussion, if it comes to it at all, the professor will probably tell you. But the theory of relativity has been experimentally tested many times and describes well-known phenomena, so there is no need to create any new theory. Exactly such a text was repeated for 1500 years by the followers of Ptolemy's geocentric theory, and they were right. The model, albeit false, correctly described the motions of the planets thanks to various mathematical tricks. Exactly like the theory of relativity, which thanks to tricks such as the derivation of the Lorentz transformation from the principle of the conservation of the space-time interval, also correctly describes most of the phenomena, and that based on a false model, in fact, hardly anyone cares. Thank you very much.